So let's look at some simultaneous equations. We've got ax plus by equals e, and we've got cx plus dy equals f. Now, with these simultaneous equations, we can express them as a matrix equation. So, ax plus by, cx plus dy equals ef. And from the definition of matrix multiplication, a, b, c, d, x, y equals ef. And we can then obviously form the augmented matrix as shown. So far, we've got this situation. And we've got down to the augmented matrix. And we can form some elementary row operations to work out what x and y are. So row 1 becomes row 1 divided by a. So let's look at what our initial matrix was. So a divided by a is 1, b over a, and e over a. Row 2 is going to be row 2 minus c times our new row 1. So we've got c minus c, which is nothing. We've got d minus cb over a, and we've got f minus ce over a. Now we can tidy that up a little bit. So as one fraction, we get ad minus cb over a, af minus ce over a. Now we can change row 2 again by dividing by this fraction, this whole thing here, to get a 1 jumping out. Now if we divide this side by all of this, this is what we will end up with. Similarly, with row 1, we're going to do row 1 minus b over a row 2. And by doing that, that will mean that this becomes 0, but we'll have all of this on the right-hand side. But we can simplify that. The main thing to notice is that the denominator of both fractions is exactly the same. That must mean something, that's special, right? And x is going to equal this, and y is going to equal this, and the denominator is the same, so these solutions are only valid when AD minus BC doesn't equal 0. When AD minus BC doesn't equal 0, we give that a special name. We call that the determinant. So AD minus BC is called the determinant. It also determines not only if solutions exist, but whether an inverse exists. So the determinant of ABCD, denoted det A, or determinant of A like this, is just A times D minus B times C. We say that if the determinant of A is 0, then A would be a singular matrix. It does not have an inverse, or if you set up a system of equations, you cannot solve those equations. There's no solution. However, if the determinant of A is not equal to 0, then A is non-singular. It does have an inverse. Here's some quick fire examples of finding the determinant of matrices. So if I've got 1, 0, 0 minus 1, the determinant of that would be 1 times 1 minus 0 times 0, which is just 1. The second one would be 1 times 4 minus 2 times 3, which is minus 2. Looking at the third one, we've got 0 times minus 4 minus 3 times minus 1. Well, that is just 3. 10 times minus 1 minus minus 2 times 4. That's minus 10 plus 8. That's minus 2. So given that this matrix here is singular, we need to find the value of P. So if it's singular, that implies that the determinant of A equals 0. So the determinant of this matrix is just 4 times 3 minus P. Take away P plus 2 times minus 1, and that equals 0. Tidying that up, we've got 12 minus 4P plus P plus 2 equals 0. 14 minus 3P is 0. So 3P equals 14. So P is 14 over 3. Given A is this, can we find the determinant of A in terms of A? And can we show that the matrix is non-singular for all values of A? Let's do the determinant first. Determinant of A, that's just going to be A times A plus 4 minus 5 times 2. Well, that equals A squared plus 4A plus 10. Part B, so it's non-singular, so if this to show that never equals 0. Lots of ways to do that. The easiest way is to complete with square. If we complete with square, we get A plus 2 squared plus 6. The minimum value of it, in other words, is 6. Positive for all values of A, therefore A is non-singular. So find the value of K for which the following system's equations has no solutions. So let's set up a matrix. We've got 4 minus 2K, K minus 3 times xy equals minus 1, 0. And remember from earlier, that meant that if the determinant of this matrix equals 0, there's no solutions to this equation. Let's call this matrix A. The determinant of A is minus 12 plus 2k squared, and we're going to say no solutions when minus 12 plus 2k squared equals 0. Easy enough to solve. 2k squared equals 12. So k squared equals 6. So k equals the positive or minus square root of 6. This has been Clear Maths. Today we've been looking at the determinant of a matrix. What is the determinant of a matrix? Where does it come from? Looking at the determinant of a 2x2 matrix. Check the next video to see how we use that to invert a 2x2 matrix.